Hello and welcome. If you're getting ready for your Math 218 final, you know there's that one type of problem that just looks terrifying, but really it's just a test of a single super powerful concept. Today we're going to pull back the curtain on that concept, eigenvalues and diagonalization. So picture this. You're in the exam, you turn the page, and you see this question. Calculate a matrix to the power of 100. I mean, trying to multiply it out by hand would be an absolute nightmare, right? But here's the thing. This question isn't about brute force. It's designed to test if you know a really elegant shortcut that's at the very heart of linear algebra. So here's our game plan. First, we'll get into the core idea of the eigenproblem. Then we'll learn the step-by-step process for finding eigenvalues. After that, we'll tackle diagonalization, and we'll finish up with some awesome exam power-ups and a special shortcut you've got to know. Let's get started. Okay, so what is the big secret to solving a monster problem like a to the 100th? Well, it all comes down to finding these special, unique vectors that a matrix interacts with in a really simple way. See, instead of twisting and turning them, the matrix just stretches or shrinks them. That's it. Think about it like this. For most vectors out there, when you multiply them by a matrix A, you're really transforming them. You stretch them, maybe rotate them, and send them off in a completely new direction. But for a very special vector, what we call an eigenvector, the transformation is just beautifully simple. Multiplying by A just scales the vector, and the number it scales it by, that's what we call its eigenvalue, lambda. The vector stays on the exact same line through the origin, and that right there is the key. Now, the best part is that finding these special vectors and their scaling factors isn't some kind of magic. We've got a rock-solid three-step procedure you can use for any square matrix. It all starts by just rearranging that main equation, ax equals lambda x, to get what you see here. Now remember, we are looking for an eigenvector x that is not the zero vector. And for this equation to have a non-zero solution, that matrix out front, a minus lambda I, has to be what we call non-invertible, or singular. Basically, it has to be a matrix that collapses space and doesn't have an inverse. And the big test for that? Its determinant has to be 0. And this brings us to the exact method you'll use on the exam. First, you set up the characteristic equation. You take that determinant and you set it equal to 0. Solving that equation gives you your eigenvalues, your lambdas. Then, for each one of those eigenvalues, you plug it back into the equation from the last slide and solve for x. How? By finding the null space. That is, all the vectors that this matrix sends to 0. Those vectors? They form the eigenspace. This is the core skill you absolutely need to master. So why do we care so much about finding all these special vectors? I mean, what's the big deal? Well, because if we can find a full set of them, it unlocks the ultimate matrix simplification tool, diagonalization. And this, my friends, is where the real power is. You can think of diagonalization as finding the DNA of a matrix. It means we can rewrite our matrix A as a product of three much simpler matrices. P is a special matrix whose columns are just the eigenvectors of A. And D is a diagonal matrix, which is super simple. It's got the eigenvalues on the diagonal and zeros literally everywhere else. And as you're about to see, this PDP inverse form is what makes calculating a to the 100th, well, almost easy. Okay, this is a huge question and a very common one on exams. Diagonalization is this amazing tool, but not every matrix can be diagonalized. So how do we know? How can we tell if we're allowed to use this tool? Luckily, there's one simple, straightforward test. It all boils down to this. An n by n matrix is diagonalizable if and only if you can find a set of n linearly independent eigenvectors. So what does that actually mean? It means you need enough eigenvectors pointing in genuinely different directions to form a complete basis for your entire vector space, Rn. If you can find that full set, you can diagonalize. If you come up short, you're out of luck. It's that simple. Okay, let's move on and talk about some serious exam day power-ups. See, if you already know the eigenvalues of a matrix A, you can instantly, and I mean instantly, figure out the eigenvalues for a few related matrices without doing any extra calculations. Seriously, you should just memorize this table. If lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse. Lambda to the k is an eigenvalue for A to the k, and lambda plus c is an eigenvalue for A plus c times the identity matrix. These are massive time savers on a final exam. All right, there is one more special case you absolutely have to know. And honestly, it's a total gift if you see it on an exam. It involves a specific type of matrix that's super easy to spot and has some incredibly useful properties. The rule is just that simple. If you see a matrix that is symmetric, meaning it's a perfect mirror image of itself across the main diagonal, where A equals A transpose, you are guaranteed that it can be orthogonally diagonalized. This is a huge result. It doesn't just mean it can be diagonalized, it means its eigenvectors can be chosen to form an orthonormal basis. They're all unit vectors, and they're all perfectly perpendicular to each other. So let's do a final review. Before you walk into that exam room, here's your checklist. Make sure you can nail the procedure for finding eigenvalues and eigenvectors. You have to understand that crucial condition for diagonalizability. And definitely remember the big shortcuts for related matrices, and especially for symmetric matrices. And we'll end right back where we started. We asked how you could possibly calculate a to the 100th. Well, now you have the key. Just think about it. What happens when you write out PDP inverse times PDP inverse 100 times? All those P inverse P terms in the middle cancel each other out, becoming the identity matrix. You're left with just P times D to the 100 times P inverse. And calculating a diagonal matrix to a power is incredibly simple. That is the power of diagonalization. Good luck on your final.